today. And we have Harry here. He's here for a little workshop that we're doing on multi-muon decays at LHCb. But he also worked on lepton flavor universality and B decays, which are currently receiving a lot of interest at LHCb. So he will tell us a bit about his part in this work, basically on the lepton flavor universality measurement involving K-short and K-star plus decays. And about your person, I don't know. You're in Cambridge and currently convening the very rare decays working group at LHCb, and yeah, together with me. And Harry has also quite a track record in outreach. Has written a book which I can recommend. So
it's been published in Spanish as well, but not Galician.
So yeah, we're looking forward to your talk.
Thanks, Titus. Well, thanks for the invitation. This I was only asked about yesterday or the day before, so I didn't have time to write a brand new seminar. So if any of you saw the CERN seminar last October, this may be somewhat familiar, but I'll try to make it interesting. Hopefully there's some of you that are not familiar with this stuff. So yeah, so what I'm talking about today are tests of lepton flavor universality in beta SLL decays. And you probably know that these transitions have been attracting a lot of interest in the last few years for various reasons, which I'll go through. I'll give some of the background in the talk. But first of all, why are we interested in these transitions? So these are transitions where a beauty quark changes into a strange quark and emits two charged leptons. And the basic idea is that in the standard model, you have these sort of loop processes, these penguin diagrams by which involving W exchange or top quarks. And then these are very suppressed in the standard model. So there are no flavor change neutral currents at tree level in the standard model. And because of these heavy particles in the loop, they're highly suppressed. So they're a good place to look for new physics, because if you have some new particle, new quantum field that comes in and mediates this process, it can give a significant enhancement to the rate, or it can affect the angular distributions or various other observables. So yeah, they're generally suppressed, branching fractions around 10 to the -7, 10 to the -6 in the standard model. The other thing that's good thing about these things is that the particles associated with the quantum fields, the new physics quantum fields that can mediate these processes, can have masses far above the direct reach of the LHC. So you can probe above the LHC center of mass energy in principle. So first of all, a bit on effective field theory. So theorists use effective field theory to study these decays. And the basic idea of effective field theory is probably familiar, but you zoom out. So you kind of treat you zoom out to the appropriate scale, which in this case is the B quark scale, so about 5 GeV, and then you integrate all the short distance physics down, and you encapsulate them in these quantities called Wilson coefficients. So you can kind of think about this, visually as kind of compressing this diagram down to a 4-point interaction. So it's the same approach as Fermi theory of beta decay. And there are 3 different Wilson coefficients that are relevant to these transitions. C9, which is the electroweak vector mediator, C10, the electroweak axial vector, and C7, which is the electromagnetic operator. And then you have the Hamiltonian, which is defined in terms of these Wilson coefficients, these C quantities and operators represented by O. So here you have the Hamiltonian written down. And the Wilson coefficients encode the short distance physics. So that's the bit we're really interested in, because presumably new physics is going to have be at high scale. And then the operators describe the low energy QCD, described using form factors. And these form factors generally have large theory uncertainties. So as you'll see, we try to construct observables that are free as much as possible of the hadronic uncertainties in these form factors, which actually is the original motivation for making these lepton universality tests when they were first proposed 15 years ago or so. So yeah, they said there's been a lot of interest in these sorts of decays in the last few years, and this is what was known in the field now as the flavor anomalies. And there are a bunch of these different anomalies, and I'll start with the dirtiest anomalies and move towards the cleaner ones. So the sort of dirtier observables, the dirtiest of these observables are the pure branching fractions of these decays. So here are some examples of branching fraction measurements of beta S mu mu transitions. So these are differential branching fractions as a function of q squared. Q squared is the invariant mass squared of the dilepton pair, or in this case, the dimuon pair. So here we have at the top left, you've got the branching fraction of B plus decay plus mu mu. So that's where your spectator quark in this beta SLL transition is an up quark. And you can see that at low q squared, so below you can see these regions are veto because it's where the Jape psi and the Charmonian resonances live, but low q squared, you can see the data points undershoot the current standard model prediction. Again, on the right, you've got beta k star mu mu. You're switching the spectator quark, it's also a vector transition, but again, at low q squared, you see again the branching fraction undershoots, and the same story with BS to phi mu mu. So these are all BS beta S mu mu transitions, but all of them you see at low q squared, there's the data undershoots the standard model prediction. The problem with this is that there are large hadronic uncertainties associated with the theory predictions. So people don't necessarily have huge confidence that these are, these anomalies are not just some, some missed theory error, essentially. Although there's been interesting work just recently on the lattice calculations for these differential branching fractions, which has actually increased the size of the anomalies. They have more presumably accurate lattice calculations, and the anomalies get bigger. So this is maybe firming up a bit. We also have measurements of, this is a sort of cleaner branching fraction. This is, a branching fraction that Titus and I and various others have worked on, which is the BS mu mu transition. This is somewhat cleaner than the beta SLL transitions. Oh, that's weird. Why is it rotated? I don't know what's happened there. Something to do with different versions of PowerPoint. Okay, what this is the invariant mass spectrum of the dimuon spectrum. You can see that there's the BS peak. And here there's various backgrounds, but you can see it's pretty clean. It's been observed. That's by LHCb. And then over here we have the summer 2020 Atlas CMS LHCb combination, which comes out at a sort of a point that's some way displaced from the standard model. Although the newer updated LHCb measurement is now more consistent with the standard model, and there's also a measurement from CMS recently. But you can use this BS mu mu is useful for constraining potential new physics contributions in these other anomalies that we see in beta SLL. Then moving to slightly cleaner observables, you also have these angular analyses that can be done. So particularly of the decay beta k star mu mu. So this is where the k star meson is a vector and it decays into a kaon and a pion. And you can construct this angular basis in terms of the directions of the kaon and the leptons in the BRES frame, and you can perform an angular analysis. And again, what you see, there's a large number of different observables you can construct for these angular analyses. The standard model uncertainties are generally smaller than for the branching fractions. And the latest LHCb analysis of beta k star mu mu, you see that if you do a combined tension by floating the Wilson coefficient real part C9, you get a deviation of about 3.3 sigma in this angular analysis. So, but again, with these angular analyses, the extent of hadronic contributions are still a matter of debate, particularly from charm loops, and that's being investigated both theoretically, and there's also analyses going on at LHCb to try and get an experimental handle. But nonetheless, it's interesting. And you have a similar picture actually in the B plus to K star plus mu mu decay. So this is an analysis from last year. And again, here are some of the angular observables, P2 and P5 prime. P5 prime is a sort of famous one where the anomaly was also seen in B naught to K star naught mu mu. And again, we're doing a similar thing where you perform fix the Wilson coefficients and you float the real part C9, you get a tension with a standard model of about 3.1 sigma. So both of these modes, these isospin partners, you see the same, interestingly, you see the same effect, essentially, the same size of effect. And then finally, the test of lepton universality. So these are measurements where you construct a ratio of the differential branching fractions of two decays where you exchange muons and electrons. So usually the ratios are usually defined in this way, where you have B to H mu mu on the top and then B to H EE on the bottom. And in the standard model, these ratios should be very, very close to 1, modulo some small corrections from hadronic uncertainties and QED corrections, but these are down at the sort of sub% level, really. So these are should be very, very close to 1. and the hadronic uncertainties essentially entirely cancel. And that was the reason for constructing these observables in the first place. So if you see a significant deviation from unity in these ratios, that's pretty unambiguous evidence for new physics, assuming you haven't screwed up your experiment. So that's why these observables are interesting to measure and why they were begun to be measured. So just to give a bit of history of this, well, actually, this isn't strictly how it happened, but the first measurement actually at LHCb was a B plus to K plus LL. And there was one done with, I think, 2011 data, and then with run 1 data. And the run 1 result came out at a sort of 2 and a bit sigma below 1. So where you have basically a suppression of muons versus electrons. Then there was an analysis done with the K-star lepton-lepton mode with 3 inverse femtobarns. That's the run 1 data set. And you measure, in this case, you measure the ratio in 2 bins of Q squared. So what we call the low Q squared bin between 0.045 and 1.1 GV squared. And then in what's usually referred to as the central Q squared bin, which is between 1.1 and 6. And the reason you do it in these 2 bins in the K star is because the K star is a vector, and that means you get an enhancement at low Q squared due to the photon pole. So you break the Q squared region in 2, and you sort of actually, you would really expect lepton, any sort of new physics contributions to be a bit more washed out in this low Q squared bin. And what you see though, again, is that this ratio is below 1, about two and a bit standard deviations from the standard model in each bin. So that was analysis that came out in 2017 on the run 1 data. Then there was a measurement of lambda decays. So similar process, lambda beta pk, lepton-lepton, this using 5 inverse femtobarns. So run 1 plus half of run 2 or bit of run 2. And again, this number, it comes out more consistent with the standard model just because the error is larger, but the shift is in the same direction, intriguingly again. This is measured between 0.1 and 6 in the case of the lambda. And then finally, the most recent, second most recent, I should say, ratio, which made a lot of news last year, which the early part of last year, which is the full analysis of B plus to K plus lepton-lepton with the full 9 inverse femtobarn data set recorded in run 1 and run 2. Again, RK this time came out at about 0.85 plus or minus 4%-ish. And it was the reason it caused the big stir is because it crossed this 3 sigma threshold with respect to the standard model. There's papers now. I show you, this is out of date. It should say it's now been published in Nature. It's not submitted to Nature. So you can also see Babar and Bell have also measured these ratios, but with much, much larger uncertainties. So this is the sort of the picture. So we have these, what seems to be a trend of deviations in the branching fractions in angular analyses and also in these lepton universality ratios. So you can do a combined global fit, and indeed many theory groups have done this, where you take these different B2SLL measurements and also BS to mu mu, and you fit for the Wilson coefficients. And what they find is that you can explain the anomalies coherently in basically 2 different ways. One where you have a new vector coupling contributing to C9, or where you have a new axial vector coupling with C9 equals minus C10, so these 2 Wilson coefficients. Here are some examples of some of these global fits and sort of the best fit points that they arrive at in planes of the Wilson coefficients. I won't go into these in much detail, but just to say there are other global fits available. There are quite a few of these things. Maybe one thing to say is, depending on which global fit you use and which inputs you use, you can get deviation from the standard model above 6 or 7 sigma in some cases when you bring all these things together, although that's a bit controversial because it sort of depends what your assumptions are and what variables you choose to include. Something horrible's happened here, but so in terms of the new physics explanations, so there are a couple of popular explanations for these anomalies, basically 2 classes of models. One involve Z prime particles, so a sort of new vector, a new vector force, which has non-flavor universal couplings. The other option are leptoquarks, which couple the second and third generation, or the second generation lepton to the third generation quarks. And these are the leptoquark models are sort of interesting, particularly as well, because they can also explain the charged current anomalies. So these are in beta d mu nu and beta d tau nu decays. But basically, some of these models also predict particles that are within the reach of the direct production at the LHC. So Atlas and CMS potentially might see these things if they exist. But we need further measurements to clarify the situation. So that's sort of where we are. And this now is, I'm just going to talk about the measurement that I made with my student John Smeaton at Cambridge over the last few years. This came out in October last year, so it's quite old now. But it's another test of lepton universality using the full run 1 and run 2 data set, but this time using the isospin partners of the two sort of modes that have the highest precision. So in this case, we have B0 to K short lepton lepton and B plus to K star plus lepton lepton, where the K short goes to pi pi and the K star plus goes to K short pi. Now, these decays are much more difficult to reconstruct because the K short has a long lifetime, so it has a tendency to fly out of the acceptance of the detector or decay too far downstream. So you get a hit in sensitivity from measuring these modes, but nonetheless, they can contribute something interesting, and you can also see if there's an isospin dependence of this effect. So these are the first measurements that have been made at the LHC with these modes, but Bell have actually done some measurements themselves, but with huge uncertainty. So uncertainty is about 50% or so. So a little bit, I'll say very brief about LHCb. Actually, I'll skip this because it's probably very familiar to everyone. But the main thing that's sort of worth bringing out, I guess, with these analyses, the main challenge you have is the different detector response to muons and electrons. So broadly speaking, muons are much easier to reconstruct. They penetrate the entire detector. They get out to the muon stations at the edge, and they're very easy to isolate and separate. And because they're heavy, they don't emit bremsstrahlung radiation, really. Electrons obviously 200 times lighter, so they first of all, they don't get all the way through. They hit the electromagnetic calorimeter and they're absorbed, but they also radiate bremsstrahlung photons as they travel through the experiment, and that degrades the momentum resolution. And it means when you measure the B mass, you get something that's much more smeared out than in the muon decay. So that's one of the main challenges. So this is we have this procedure at LHCb to try to correct for this problem of bremsstrahlung radiation. So here's a little cartoon of what happens. So you have your electron coming along from the primary vertex, you have the magnetic field, and then you have your calorimeter. And there are two different things basically that can happen. One is where the electron interacts with some detector material, maybe in the tracking system, and it emits a photon. And that photon, bremsstrahlung photon, will generally carry along going in the direction of flight of the electron. So it just goes in a straight line, and it hits the electromagnetic calorimeter over here, and the electron then bends in the magnetic field and ends up over here. So the way the bremsstrahlung recovery process works is it looks at the track of the electron before the magnet, extrapolates it into the calorimeter, and it looks to see if there is a cluster at that location. And if there is, that energy of that cluster is added back to the momentum of the electron track, and that helps you to recover at least some of the lost resolution. The other option, of course, is the electron gets through the magnet and then it radiates a photon afterwards. If that happens, it doesn't really matter because it doesn't affect the momentum because you've already got the curvature, and the cluster of the photon ends up in the same place as the electron, so you get the full energy essentially. Yeah. So this gives you an example. So even after Brem recovery, you still have a much poorer mass resolution for the electrons. So these are the B invariant mass for the B plus to K plus lepton analysis. So not the one I'm talking about, but the one from early last year. You can see for the muons, you've got this nice clean sort of Gaussian-like peak. For the electrons, it's much more smeared out. You've got this long tail, and you've also got a whole lot of junk at low mass as well that you have to deal with. Notice that the ranges of these plots are different. So we're going down to about 4.9 GeV, but here we're cutting off the fit at 5.2. So you have to go lower to capture this radiative tail, and that means you then have to account for these partially reconstructed backgrounds and other things that live at low mass. So it makes the electron mode basically just more challenging to deal with because of this bremsstrahlung effect largely. And they also have a problem that the efficiency to select electrons is only about 20% of that for the muon modes. And that's also partly because the electrons have a tendency to get swept out of the detector acceptance by the magnets. You get a hit in efficiency because of that. And so controlling the differences essentially in these efficiencies and these bremsstrahlung issues is the main challenge for these analyses, if you want to make an unbiased measurement. So the way this is done generically is you measure these ratios, lepton universality ratios, as double ratios with respect to control modes. And the control modes are essentially the same, similar to the rare modes, except the dilepton pair comes from a J-psi resonance. So you have in beta J-psi K usually. And the J-psi can decay either to electrons or muons, and it does that at a pretty much equal rate, modulo phase-space effects, but very close. And they have a branching fraction that's about 1 in 1,000 or so, but they have much larger, the control modes have much larger branching fractions, obviously, than the rare modes. So you construct this double ratio where you take a ratio of the yield of your rare muon mode divided by the yield of the rare electron mode, and then you have the opposite ratio, but this time with the control modes, and then the same thing with the efficiencies. So you have this sort of double yield ratio and double efficiency ratio on the other side. And basically, there are only 2 bits to the analysis. The 2 bits are get the yields of the 4 modes, so the 2 signals and the 2 controls, and get the efficiencies. And you've made the measurement essentially. And what's good about this method is that most of the system, or many of the systematic effects, cancel very precisely in this double ratio, because your control and signal modes have generally pretty similar efficiencies. So it makes it pretty robust against potential biases. So there are a number of aims to this analysis. First of all was the first observation of the electron modes, because they've never been seen before unambiguously. So we wanted to make an observation of beta k short EE and beta k B plus to k star plus EE for the first time, and also measure their differential branching fractions. So in the case of differential branching fraction, this is done just with respect to the electron control mode, as opposed to the lepton universality ratio. So skip something there? No, that's all it was. Okay, right. So so for the signal modes, the Q squared selection that we use for the K star plus mode, we take this wide bin between 0.045 and 1.6 rather. And this is essentially due to boost our statistics, because we need to observe the rare mode, and it's difficult to do that in just the central bin. So we widen the K star modes Q squared range. For the K short, we just do it between 1.1 and 6, because you don't have this photon pole enhancement in the case of the pseudo scalar decay. And then for the control modes, you have basically a Q squared bin around the J psi mass. It's narrower for the muon mode and wider for the electron mode because of the poorer resolution. And then for the K star, we take a mass window of 300 MeV in either direction around the mean of the K star peak. So this means, this is a plot actually of the K pi invariant mass from B naught to K star mu mu. And what you see here is that you don't just get the vector, you also have this S wave continuum underneath the peak. So there's about a 22% S wave component coming in as well, which is included in the analysis. So it's just worth bearing in mind when you're thinking about what the exact meaning of these differential branching fractions are. So the selection, so there is first of all, we have the trigger selection. So the muon trigger selection is very simple. We just require that one of the muons at least is selected by the level 0 muon trigger in hardware. For the electron, we have 3 different trigger categories. One where the dedicated electron trigger fires, one where it's fired on the hadron. So in that case, the K short, or possibly the Bachelor pion for the K star. And then finally, we also select events where some other part of the event independent of the signal fired the level 0 trigger. And that maximizes our statistics as much as possible for the electron mode. Then there are high level triggers in software. The first level trigger essentially looks for a single track, which has a high PT and high impact parameter. And then at the second level, you have various topological triggers that look for B decays. And that's how we select the different signals. Then for the actual selection, we construct the candidates by combining a displaced dilepton pair in your event with a K short candidate, and also an extra pion if it's the B plus. There are requirements on vertex quality, momentum, separation from the primary vertex, and so on to suppress combinatorial background, so random background. And then you have a boosted decision trees. Machine learning, very simple machine learning algorithms that are trained on data and simulation, and they are used to suppress combinatorial background. So in terms of those backgrounds, you have backgrounds from misreconstructed B hadron decays, and these are, broadly speaking, reduced to negligible levels by kinematic mass and PID requirements. So you have, for example, decays of the form B hadron goes to HH lepton lepton. So this is where you have essentially the dihadron pair is produced at the B vertex, unlike the K short, which flies and then decays into 2 hadrons. So that's quite easily rejected just by having a flight distance requirement on the K short. You have contamination from lambda decay. So obviously the lambda beta lambda lepton lepton, the lambda has a long lifetime, so it flies like the K short. So combination of mass window cuts around the lambda mass and also vetoes on proton PID to get rid of those. And then you have these rather nasty collection of decays known as what we call cascade decays. So it's where a B meson turns into a charm meson, and then which decays into a K short, some combination of electrons or pions. And that gives you essentially a low mass background below the B mass, where you're usually missing some neutrinos or you've mis-ID'd something. But you can get rid of those with vetoes on the D mass, usually quite efficiently. And you have analogous modes for the B plus with some other details that I won't go into. In terms of the background, that's sort of irreducible and are modeled in the fit. So for both modes, you have partially reconstructed background. So that's background where you miss a track. So for the B0 mode, actually the B plus signal is a background. So basically this is where you have your K star decay to K short pi and you miss the pion. Then it just looks like your B0 to K short mu or lepton decay. So that gives you a shoulder at low mass. Similarly for B plus, where you have higher K star resonances that go to K short pi pi, for example. So you have this low mass background, which you can't really get rid of. So you have to fit. And then there's also double mis-ID background, particularly, this is for the electrons really where it's relevant, where you have decays like B0 to K short pi pi, where the two pions can be misidentified as electrons. Now, that's again quite hard to, it's dangerous particularly because it's sharply peaked because pions don't radiate Bremsstrahlung radiation to a large extent, so they have good resolution. So they actually peak directly under your signals. You have to be quite careful. So these are estimated. There's a small about 6%-ish contamination left that's then included as a component in the fit. And the contamination is estimated from a combination of simulation and also data-driven corrections to get the PID efficiency for these modes. Yes, so efficiency calibrations. This is actually where the bulk of the analysis lives, basically. This is the hardest bit. So where you're trying to essentially make sure your simulation accurately represents the data, so you can trust the efficiencies that you take from the simulation. So the simulation is corrected using this great long chain of reweighting procedures that you apply to improve the agreement with data. The first thing that's done is that the PID requirements, this is information from the muon systems, the rich calorimeters. It's not very well modeled in LHCb simulation. So in general, we take these efficiencies from calibration samples of pure electrons, kaons, pions, muons in data. So that's the first thing that's done. There's a correction for the electron tracking efficiency, again, that's used using a data calibration sample. The kinematics of the generated B hadron in simulation is also not that well modeled. So this is corrected using the control mode. So essentially you have this high yield control mode and in data, which you can get a very clean selection on. And you basically do a background subtraction, look at its kinematic distributions, compare that with your simulation, and you get weights to correct your simulation overall. Similar story with the event multiplicity. Again, the simulation doesn't model the number of tracks and the noisiness of the event particularly accurately. You correct that again using your control mode. The K-short mesons, because they're long-lived, we have two different ways of reconstructing them. One is where they decay in the vertex locator, where you have, which means in the velo, the front of the detector. Then you have a long track that goes all the way through the experiment. The other possibility is they decay after the velo in the first tracking station or before the first tracking station, where you don't have a velo track, but you only have this sort of first bit of the track before the magnet, and that's called a downstream track. So you have K-shorts in both of those categories. And again, we perform a correction to make sure that the proportions of those map between data and Monte Carlo. Actually, this correction is very small. They pretty well are actually, it's pretty well modeled actually, in fact. The trigger response is corrected, again, using the control modes to make sure that the description of the trigger is well represented. And then finally, the BDT response is also corrected using the control mode. So you have this great long chain, essentially. Oh, I'm sorry, one more. And the Q-squared resolution. So there's a small difference between the Q-squared resolutions, the resolution on this invariant mass squared of the leptons between data and Monte Carlo. And again, this is corrected using the control mode, but it's quite, actually, that's a pretty small effect overall. But you apply all of these corrections, then hope, oh God, hopefully, I thought this is very strange. Once you've done that, the idea is that you should then be accurately modeling your efficiency ratio, which is the key thing. So what I'm trying to show you here are the maximum likelihood fits used to extract the yields of the control modes. So this is the, oh God, this is really mangled. these are the, okay, at the top you have the muon control modes. That's the K star plus, that's the K short, and these are the electron control modes. So, okay, I mean, it's a bit hard to read, but what you can see is actually both of you, what's interesting, what's worth noting is that for these control modes, the peaks for both the muon and the electron modes are pretty sharp. And the reason for that is that you can put a constraint on the J psi mass. So you actually recover a lot of the lost resolution in the electron mode, and you get this much tighter peak with almost, and you can see also there's basically no background. These the control modes are very clean. So that's where you get your yields from your control mode from. I wonder if I can switch. Have you got the PDF actually? I don't know if it's worth.
Yeah, the PDF is also here.
I think it's also on the, yeah.
Okay, so maybe then I
Might be
stop
worth it.
here.
If the rest of the presentation will be on its side, it might be worth it.
Yeah, okay, so I can stop sharing and open the PDF. It's the other one, right?
Yeah, yeah, hopefully it's all yeah.
Okay, then I go back. Okay, and now how I go to full screen?
Yeah. Cool. Right. Oh, well, there we go. Oops, sorry, getting in the way. There we go. That's better. We did this anyway. That's fine. Okay, so this is the rare mode now. Invariant mass fits for the muon rare modes. Again, obviously here you don't apply a J psi mass constraint because there's no J psi involved, but you can apply a constraint on the K short mass, which gives you a bit of an improvement. It's not big, but you get a small improvement. The parameters of the shapes for the signal taken from simulation, and also we allow shifts in the mean and width for the peaks based on fits to the control mode data with respect to simulation. But what you can, these fits are pretty simple. You've only got your signal and the combinatorial component, so they're pretty straightforward. And you get yields of about 100 events for the K short mode or B naught mode rather, and about 200 for the B plus. Anyway, that's pretty straightforward. And then here are the electron mode fits. So as you can see, it's a lot more messy. This should have appeared later, doesn't really matter. It's the same story basically, but you've got a lot more stuff going on in this fit. So the red dotted line is the signal. You can see at low mass, you have this rather ugly, is it brown or green? I'm not sure. I don't know who chose that color scheme. This is the partially reconstructed background, so where you're missing a pion. And then you've got this blue sliver, which is actually leakage from the J psi control mode. So because of the long radiative tail of the J psi, some of it leaks down into the low Q squared region, and that piles up at low mass. But you can estimate that very precisely because you know the control mode yield in the control mode region, and you can just kind of make an extrapolation, basically. And then this little gray bump that you can see, that's the double mis-I dihadronic background. So the K short pi pi or K star plus pi pi. And what's nice is that when we unblinded this fit, we didn't really know whether we would get 5 sigma, but we did for both of them. So you get 5.3 sigma for the K short mode and 6 sigma for the K star plus mode. So that's the first observation of these channels, which is quite nice. And then we move on to the systematic uncertainties. So the dominant systematics actually come from the statistical uncertainty on the efficiencies. That's basically just limited by the size of the Monte Carlo samples that we were able to generate, about 2 to 3%. But as you'll see, that's pretty small compared to the statistical uncertainty. The next, the dominant systematics, we have the size of the simulated candidates used to determine the PDF shapes, again, and then the model used for partially reconstructed and J psi leakage background, so sort of choices, exact model choices you make. And then a whole list of subdominant effects that come in, which I won't go through all of them in great detail. So validation. So one of the things we really want to do with this analysis is to actually be confident that we have these efficiency ratios under control, because that's key, and that's what this whole suite of reweighting was for. So we make measurements of other ratios. So we make a measurement of a double ratio referred to as R psi to S. So this is where you switch the rare mode for the equivalent psi to S decay. So this is beta psi to SK, where psi to S goes to EE or mu mu. And now obviously this has a different kinematic phase space because the psi to S lives above the J psi, but it nonetheless, it gives you some confidence that you're getting your efficiency ratios right. These are the fits to the Psi2s muon mode and the Psi2s electron mode for the B naught. And you can see it's a bit different looking. You've got this sort of funny shape at high mass due to J psi leakage in the other direction. This is going up in Q squared effectively. But what you find for the K short mode is that our Psi2s comes out as 1, with a precision of about 3%, and it's well within the uncertainty. So that gives you some confidence, consistent with unity. Same story for the B plus mode. Again, you measure this double ratio and you get a number that's nice and consistent with 1. So that suggests that, at least in this regime, that the efficiencies are nicely under control. And then there's a much more stringent test which we perform, where we just do a single ratio referred to as little r j psi. And this is where you remove the signal mode and you just check that you get the branching fraction ratio of the 2 control modes coming out equal to unity. Now, this is more stringent because you don't have this cancellation effect. You're basically taking a single ratio of electrons to muons. And that means that if this looks good, that again gives you confidence your efficiencies are under control. And what we find for RJ psi is that both of the measurements for the B naught and the B plus mode, again, come out pretty well consistent with unity within the systematic uncertainties. So again, that gives you quite a lot of confidence that you've got everything under control. One other thing that's done is also we look at this observable RJ psi differentially as a function of various variables. Particularly, we choose variables that have substantially different distributions between the signal and control mode. Because if RJ psi varies as a function of these variables and these variables don't have the same distributions in signal and control, that could introduce a bias into your double ratio. So we pick, these are 2 of the most discriminating variables. So the dilepton opening angle, the angle between the 2 leptons, which is quite different in the control and signal because the J psi has a larger mass, so the opening angle tends to be smaller, whereas the lower mass, lower Q squared region, it's wider. And then also we have an MVA that we train on Monte Carlo to distinguish control and signal modes from one another. So that's in some sense the maximally different variable that you could have. And what you see, at least within the statistical precision, there's no real evidence of any trends here. It's just sort of random noise. So again, that gives you confidence that there's not some nasty pathological effect that affects your double ratio. So so we obviously, I said that we observe these rare electron modes, then we also make a measurement of their differential branching fractions in these Q squared regions, which are given there. And then the actual thing that we're already interested in, which is the lepton universality ratio. So on the left-hand side, you have the results for the B naught mode, and on the right-hand side, the results for the B plus. And what you see here is the likelihood projection for RK short, and on the other side, RK star plus. One thing I should point out, we actually measure the inverse ratio. So we flip the ratio around so the electrons are on the top and the muons are on the bottom. And the reason is because the electron mode has a lower yield. You have a more Gaussian error if you have your low yield thing in the numerator, not in the denominator. But you can straightforwardly convert these numbers into the sort of more familiar arrangement. When you do that, you get 2 numbers that are consistent with the standard model at about 1.5 standard deviations. But the shift again is in the same direction as with the other measurements that I went through at the beginning of the talk. So, 1.5 sigma is nothing to get terribly excited about, but it's interesting that they are shifted in the same direction again. We also perform a combination of these 2 measurements just to see what the combined significance with the standard model is. And this is done using the package Flavio, and we fit for the Wilson coefficient. So we make this choice where we float C9 equals minus C10. And that's because these ratios can't actually disentangle C9 and C10 on their own. So we just set them to be, we make this assumption. When you do that, you get a combined significance of 2 sigma. And the best fit value for C9 is just given there for interest. And then this plot on the right-hand side shows the sort of state of these measurements compared to the existing measurements by Bell. And you can see, it's a substantial improvement on the uncertainties that were previously published. So that's it really. So the conclusion really, we've got these first observations of these rare electron modes and these decays, most precise measurements of their differential branching fractions at low Q squared, and also the most precise tests of lepton universality in these modes, which come out just below 1 with about 1.5 standard deviations from the standard model. Same pattern as deviations as seen in other LFU tests. And the other thing to say is there are lots of other LFU tests in progress at LHCb, hopefully some news coming soon with updates with a full run and two data. So yeah, stay tuned. Thanks for your attention.